All right, welcome back to the materials 2Q03 electronic properties of materials um, course overview slash exam review session. This is the third and final video that I will be recording. This is going to give you all the information and knowledge that has been gone over in class, at least in my year, after the second midterm. We left off, I just moved everything up a little bit. We left off talking about the Fermi-Dirac function, effective mass, and metallic color. And now we're going to get right into conductivity. Now, all I'm going to say before we get right into things is that we're going to be going over three main models in this video. All these models contain contributions from thermal and electronic properties. As for the electronic properties, the model for all three have very similar theories to them. So if you know one theory, you're going to be good with all of them. So before we get too theoretical into things, we're just going to go over macroscopic conductivity. And when I refer to conductivity in this video, I'm going to be using the symbol sigma. Now, this is something that you've probably seen in prior physics courses. There is one main way to describe Ohm's law. The one you were thinking of is probably V is equal to IR. Another way actually to express Ohm's law is using current density J being equal to sigma the conductivity times the electric field. Now the electric field can be described using several different formula. The first one being the voltage that you apply to a length. So if I apply a voltage to a wire, this wire is going to have an electric field. Another way to describe the electric field is by rearranging this equation that I drew out. Also, another way to describe conductivity, though, is by using the number of free electrons that you have in your metal multiplied by the velocity of these electrons times the electronic charge. Putting these, not sigma, I meant to say current density. Now putting these together, if we were to equate them and solve, we would get a function for sigma using the free electrons, the velocity, electronic charge, and our electric field. This particular fraction, velocity divided by electric field, is what we call the electron mobility, U of E. Now let's pretend that we're to be given a wire. This wire is going to have cross-sectional area that we're going to call S. This wire is also going to have a length to it. And whatever metal that we use is going to have a certain resistivity. The resistance in this wire is equal to the resistivity of the metal that we're using, multiplied by the length of the wire, divided by the cross-sectional area S. Moving on, we're going to talk about how electrons move across a metal and how we know that metals are conductive. What it looks like inside of the metal. And this is going to be using the classical Drude theory of conductivity. Now let's pretend we were given a plate of metal. We know that this plate is going to have a bunch of electrons in it. Now, without applying a potential energy, these electrons have no desire to go any which way. So they're just kind of floating in space here. They're not really doing anything. They're going in different directions. As soon as we are to apply a potential in this plate here, if we were to say apply a potential that looks like this side being negative and this side being positively charged, We know that the electrons want to go from the negatively charged side to the positively charged side. So the electrons are pushed in a direction which causes them to drift towards the positively charged side. And this is called our drift velocity. We can calculate this velocity by making it equal to the electronic charge times the electric field applied, divided by the mass of our electrons, multiplied by whichever time we are at after this potential is put onto this plate. Now, what we know about electrons in metals is that a imperfect metal, which is like any metal that we see in real life, a crystal, if you will, in these crystals, I'm going to draw a little bit of a lattice here, actually. There are lattice defects. There might be some missing atoms where there should be one. If I were to draw a little bit more, maybe it'll look like this instead. Right? There are missing atoms, right? Defects. These defects are going to cause the electrons moving as a wave to scatter. So if an electron is being propagated here, it'll scatter when it sees a defect. After a long time, though, the velocity kind of equalates, and all the electrons are scattering on those defects, right? And this is what it looks like here. If we were to split up this graph into short time and a long time, and we were to say that the y-axis is velocity and the x-axis is time. Over a short period of time, our velocity would increase with respect to this t variable here. Over a long period of time, this curve would flatten out, and our velocity would be equal to the maximum velocity. If we were to model this a different way, we would say the velocity of our electrons is equal to the velocity of the free electrons multiplied by 1 minus the exponential of negative charge times the electric field divided by the mass times the free electron velocity times t. This thing here is what we call tau, our relaxation time. Our relaxation time is equal to electron times electric field divided by mass times free electron velocity. This is how many collisions, or this is how many seconds are between each electron collision with a defect. If we were to take this tau value and multiply it by the free electron velocity, we would get the mean free path. And this is the length each electron goes before it collides, meters per collision. Now taking these two values and creating a new equation for our conductivity, we can say it's equal to the number of free electrons we have times the electron charge squared divided by the mass times tau, our relaxation time, or the number of free electrons times our electronic charge divided by mass times our velocity of free electrons divided by our mean free path. Now this is what we call the classical theory. We're now going to get into some quantum mechanics. Now we're going to go back to the density of states model that we saw in an earlier video in part 2 of this review session. So if you recall, it looked a little something like this. You had energy on the y-axis, density of states on the x-axis. And then we had here our parabolic function. That doesn't seem to want to work for me. There we go. And at a certain point, we had a Fermi energy. Okay, now, when we talk about conductivity, we know that electrons in the conduction band are what we call conductive electrons. And in this specific case, when we're using the Drude theory, we're talking about metals. Now, what do we know about metals? Well, let's pretend that this is our conduction band. And this purple one is our valence band. We know that these bands overlap. Now, we also know that the valence band is full of electrons. We would also say that this thing here, that's our Fermi level, right? That's the highest point an electron can be at. Now, if we zoom in, we would see that in this box here, all of these electrons can be considered conductive electrons, right? But the electrons near the top of the conduction band have more energy than the electrons near the bottom of the conduction band, right? They have more energy, they're more excited. Now we say in quantum mechanics that only these electrons that are close to the top of the conduction band can be used in conductors, right? Because all of these other electrons are kind of being squished down by each other, right? And they wouldn't really be useful to us. So only the electrons close to the top and at the Fermi level can we use for conduction. Cool. Now, what we do is we apply a few quantum mechanic rules. We're going to say that if we take this little chunk to be dE, and we take this little slice to be dN, we wanted to know how many electrons are in our dN. So dN is the number of electrons per energy level. So we're going to take the number of electrons we have at our Fermi level, and we're going to multiply it by our dE, our little energy level. So we have a little energy level, we have our density of states at that energy level, and we're going to multiply together to see how many electrons we have there. Now, this quantum mechanical model of conduction says that conduction is equal to 1/3 electronic charge squared times the density of states at the Fermi level times the relaxation time times the Fermi velocity squared. This Fermi velocity is how fast electrons are moving when they are at the Fermi level. Now, something pretty important is what we call our effective number of electrons, NEF. Now, this value is how many electrons are being used when we're talking about conduction. It's used by this equation here. And this dE over dK is usually used at our Fermi level. Now, this equation, it's fine, but I like to graph this. I think it's very useful to graph this. So we're going to use the model that we know about our bands in particular is that they're scattering at the Brillouin zone, right? Whether it be a semiconductor, a conductor, an insulator, there's Brillouin zones, there's area where it can be conductive. There's always scattering at the Brillouin zone. The difference between a semiconductor and a conductor is how far the gap is between in the degenerate states. So if I were to draw what that band would look like, it would look like this. And let's draw our Fermi level really low for now. We'll work our way up. So this is our Fermi level, and we want to know the effective amount of electrons. Well, we know that our effective amount of electrons is proportional to the derivative of our energy with respect to our wave vector. And what do we know about this graph? Well, we know the y-axis stands for energy, and the x-axis stands for our wave vector. So if I'm right here, let's take the derivative at that point, or the tangent line directly at that point. It looks like that. Not too bad, right? Obviously, it's not the highest sloping thing in the world, but it's not awful. Now, let's try that again. Let's go a little bit higher. We'll go up here. Say this is our new Fermi level. What's that going to look like? Well, we have a higher Fermi level, so our electrons are in a more excited state. They have more energy. And when you know our tangent line there is a lot more steep. It looks like that. So there are going to be a lot more effective electrons there. Now, let's say we were to have a full valence band or a full conduction band, right? This full band, this final full band we know is our valence band, right? So if our final band in our metal or in our material is full, we know this is our valence band, right? The final full shell. This is our final full shell, then the derivative at our Fermi level here looks like this. And what's that derivative? Well, we know that derivative is 0. So what kind of material must this be? Well, it must be an insulator. Very good. Hopefully you said that with me. Now there's 3 types of models that we just went over. The first one we went over was bivalent. That was the low Fermi level. So low effective electrons. The second one we went over was monovalent. High Fermi level. High effective electrons. And the third model we went over were insulators. Where the derivative of energy with respect to K is equal to 0. Now, we talked about resistivity earlier, but we don't really know what it is. Well, all it is it's the inverse of conductivity. Very easy, right? And we already went over how we can describe resistance with resistivity given a wire. But how do we get to resistivity? Well, we know it's a material property, but it follows a certain rule. Mathiassen's rule. And this one says the resistivity in total is equal to the thermal resistivity plus a residual resistivity, which breaks down to resistivity due to impurities and resistivity due to defects. this resistivity here is due to phonons, which we'll get to a little bit later. Now, we're going to take a little bit of a look of what the resistivity due to impurities and defects. Sorry about that. Resistivity and defects look like a little bit later. But let's look at what our thermal resistivity looks like. So we know that we're going to have some residual resistivity. So that's going to bring us up at 0 Kelvin. It'll bring us up to this point here. So this is resistivity, and this is temperature. At a very low temperature, our resistivity is kind of flat. It oscillates a little bit. It's in the T to the 5 range, right? So very, very low. Now, as T increases, phonon scattering increases, which we'll get to that later, but we end up getting a linear model. Now, in short, there's two main rules that describe how resistivities work due to impurities. The first one is Lenz's rule. This states that the change in resistivity is proportional to the valency of alloying elements. Meaning if I had a matrix of copper and I added something with a low valence of electrons, it wouldn't add to resistivity as much as if I were to add something with a high amount of valence electrons. We also have Norheim's rule, which is just a mixing rule, believe it or not. It says resistivity is equal to the mole fraction of A times the resistivity of A, plus the mole fraction of B times the resistivity of B, plus some constant C, multiplied by XA, XB. Now, I want you to try to answer this question. This would be a very good multiple choice question to give on a test or exam. Let's say I were to have resistivity of copper down here and resistivity of gold up here. If I were to try to draw a line between this point here and this point here, what would that look like? Would an A look like a straight line, or B, parabolic? I'll give you a second. Hopefully you answered parabolic, because we're looking at that, what we just drew here. We do see linear in these two, but we know that we can express a mole fraction of A and mole fraction of B by just taking 1 minus the mole fraction of A, multiplying that by the mole fraction of B. We will get a function that is parabolic. And we'll say that this is XB. Now, what's cool about Norheim's rule is it includes something a little different that we don't see. At specific points, there's major dips in our resistivity. And this happens at particular compositions. You don't need to know exactly which compositions there are. It's just good to know that there's these certain dips. Now, if we expand Mathias's rule, Mathias's rule, we get that the total resistivity is equal to, get ready for this, the thermal plus the vacancy plus the interstitial, plus the dislocation, plus the stacking folds, plus the grain boundary, plus the surface, plus the solutes. A lot of contributions. Luckily, most of them follow, well, they all follow a very similar model. I'm going to loop together resistivity of vacancies and resistivity of interstitials. They're both equal to a concentration factor, concentration of vacancies or resistivities, times a specific scattering factor. Now, this specific scattering factor tells us how much an electron scatters given an interstitial or a vacancy. And they're the same. So if I have a wave propagating and it meets an interstitial, it'll scatter. That tells us how much it scatters. Next, we're going to look at the density due to dislocations. This is equal to our concentration of dislocations times our specific scattering of dislocations. Our concentration of dislocation is equal to the length of our dislocation line divided by our total volume. Our resistivity due to vacancies, due to grain boundary is equal to our resistivity due to stacking folds, which is also due to our surface resistivity. These are all equal to some constant value times some specific scattering value. This constant is equal to area divided by volume. The final part is the resistivity due to our solute elements. This is equal to some P naught value, which is the resistivity due to 1% of a solute atom, times by the percent of solute. So if we were to be given 3% of a solute element, we'd have to multiply our P naught value by 3. The next thing we're going to talk about is the work function. This can be kind of confusing, so I'm going to try to explain it as well as I can. If we're given a metal, we know that this metal has a certain maximum energy, the Fermi energy. But there's a space between the Fermi energy and the surface energy, or the energy at the vacuum. This space is what we call our work function, the energy between the vacuum and the Fermi level. If we were to have another metal, and we were to say its Fermi level is maybe down here, it has a lower Fermi level, therefore a higher work function. The cool thing about these metals is if we were to put them together, their Fermi levels would meet in the middle and equalize, but their work functions would stay at the same level, giving a potential difference. That looks like that. What this junction looks like, this is called a junction, by the way, is if we are given those two metals, with one metal having a higher work function than another, meaning it has a lower Fermi level. We know that the electrons want to go to a place with a lower Fermi level. The electrons want more space to move around. So let's say the metal on the left has a lower Fermi function. So it has a lower work function, so a higher Fermi level. This means the electrons want to move to where there is a higher work function or a lower Fermi level. What does this mean? Well, it'll leave the side with electrons leaving with a positive charge and the side gaining an electron a negative charge. We're now going to talk about thermoelectric effects. The first one we're going to talk about is the Seebeck effect. Given two temperatures, T1 and T2, along with two metals, if T1 and T2 are equal, nothing really happens. The charges equalize. We're all good. However, if I were to say add heat into T1, so T1 is now greater than T2, electrons are going to want to travel. Now we know that because of what we just did, making one of the metals positively charged by making that junction, and one of the metals negatively charged, electrons are going to want to move in one certain metal. When the electrons are given so much thermal energy, they're going to want to move to some place where there's less thermal. And they're going to take the route with the most positive charge. We also know that some electrons are going to want to travel through this metal as well, but not much do. This happens until the temperature at T1 is equal to the temperature at T2. The second thermoelectric effect is the Peltier effect. Let's have something different happening this time. Now I'm going to place a battery right here. We know that the electrons are going to want to travel from the negative terminal all the way over to the positive terminal, just like that. We also know that electrons have a lot of thermal energy. So as the electrons go from one metal to another metal, they're going to give T2 a lot of thermal energy because there's an influx of electrons in T2. As they go towards the positive side, they're going to suck electrons out of T1, right? Making T2 heat up and T1 cool down. All right, we're now going to talk a little bit about thermal properties of solids. In this class, we're specifically talking about the case of metals. So just to avoid any confusion, just remember, whenever I'm talking about these properties, I'm using metals as my examples. We know that a change in energy is always equal to a change in work plus the change in heat in the system. In this class, we're going to assume that the change in work is always equal to 0, meaning a change in energy is always going to be equal to the change in heat in a system. When we talk about heat capacity, we're going to talk about specific heat capacity. Since we're talking about energy in the form of heat, we're going to say specific heat capacity for constant volume is equal to the change in heat with respect to temperature, which we know is equal to the change of energy in our system with respect to temperature, where V is constant. V as in volume. CV is just a specific heat capacity for volume. So specific heat capacity is in units joules per mole Kelvin. We want to get this and this kind of specific heat in terms of per mole. This might not be asked. This was very lightly brushed over, but specific heat capacity is equal to specific heat capacity at a constant volume is equal to the specific heat capacity at a constant pressure minus the thermal expansion coefficient squared times temperature of the system times the volume of the system all over the compressibility of the system. Again, that was touched upon in lecture, but it might not be super important for any test or exams since we weren't really expanding upon that. What we did expand upon a lot was the Dulong-Petit theory. It was proven that as a specific heat capacity in solids, I'm going to start with our temperature. As our temperature approaches room temperature, 298 K, our specific heat capacity in solids approaches 25 joules per mole Kelvin. It does this in a cubic-like fashion. So if I were to draw my graph here, for temperature being a function of specific heat capacity, I'm going to draw a line where this is 25 joules per mole K. When I draw my function for temperature as for specific heat capacity as a function of temperature, it looks a little something like this. That cubic function that draws an asymptote at 25 at around 300 Kelvin. 298, 300, just like that. Now, the classical model that we're going to be using is the ball and spring method. So if we were to have our ball like this, being an atom, a spring in the middle attached to another atom here, if we were to add energy to the system, the spring would start oscillating faster, meaning there's more thermal energy. We model thermal energy like this. Boltzmann constant multiplied by our temperature. This is what it looks like in 1 dimension. If we want to model this in 3 dimensions, well, all we're going to do is we're going to multiply our value by 3. Now, what do we know about a ball and spring from our classical physics? Well, it has a potential energy and a kinetic energy. Now, what are these potential and kinetic energies? Well, we know that they're split evenly. So if we know that our total energy is 3 Boltzmann constant temperature, our potential and our kinetic are split evenly, and they're both 3/2 Boltzmann constant multiplied by our temperature. Now, if we were to try to find our specific heat capacity in the term of the 3D model, we would have to do two things. First, we would have to take the derivative of our energy with respect to temperature, which would give us 3 Boltzmann constant. But if we want to find per mole, we're going to have to multiply it by Avogadro's number. If you plug this into your calculator, you'll see that it's about equal to 25. So our theory works. Now we're going to move on to the quantum mechanical model. Now, the quantum mechanical model, we start by considering Einstein's method. And he said, okay, we know that we have a certain energy from these oscillating atoms. We're going to have to give a quantity to this. We're going to have to quantize these oscillating atoms, that energy. Now, what he did is by quantizing them, he made that energy into what we call a phonon, which is kind of like a particle, right? It's a certain kind of boson. These particles follow fundamental physics. It has a wavelength, it has obviously an energy, it has momentum. And we would be able to find this just like how we would for an electron. Now, he said we're going to quantize the energy at oscillating atoms by taking our total energy to be equal to our potential plus kinetic, just like normal, right? Now, he found a way to say, okay, our total energy must be equal to our h dash times our angular frequency, the frequency at which we are vibrating at. And if we were to apply this to a quantum mechanical model, we know that we have to apply this per energy level, right? When we quantize something, we do it in small finite values. So we're just adding an n to this. Now, what does this mean? Well, the interesting thing about this quantum mechanical model is that all the energy levels are spaced evenly. If you refer back to the other videos, we saw that some quantum mechanical models were spaced by n squared, some by 1 over n squared. This one is just spaced by h omega. They have the same spacing. Now, phonons, like I said before, are bosons. And they use a different kind of statistics. The number of phonons, or the probability of having a phonon, is equal to 1 over our exponential times that thermal energy over kT minus 1. This is the model that we use because they do not follow the Pauli exclusion principle. This means that multiple phonons can have the same principal quantum numbers. They can have the same energy. They can be at the same energy level. Sorry about that. Now, the energy of our oscillation, or the energy of our phonons, we can say in one dimension it's equal to h dash omega times the number of phonons that we have. And Einstein's theory says that this frequency is a constant. The frequency at which our atoms oscillate at is a constant value. And this happens at a certain temperature. Now, if that doesn't make sense, that's fine. Now, so what happened was we found an energy statement right here. From there, we know that the number of photons is equal to this equation. When we take the derivative of that, we get an expression for our specific heat capacity. And it's a long expression. Yes, it's a long one. So that's the expression that he came up with. So this theory works to an extent. If we go back up here and we see that this red line is the experimental line, right? This is the line that we got due to experiments. This is the line that the Einstein theory predicts. Similar, yes, but there's an offset. So it's not super accurate. Then this dude named Debye came in. And his theory is a little bit more accurate. So he quantized the phonon in a slightly different way. This is how he quantized the phonon. Not so much different, just adding a constant. Now, what he did that is really different is he said the energy that a phonon can have isn't constricted to one kind of omega value, not constricted to one kind of frequency. We can have a whole bunch of frequencies spanning from 0 to some maximum frequency, which is the Debye frequency. And that's equal to the energy of oscillation times the density of our phonon modes, which are the different frequencies it can be, d omega. We also have this new term now called the Debye temperature. This is the maximum temperature that you have. Sorry, this is the temperature that you have where the maximum frequency is. Now, after solving this integral and then taking the derivative with respect to t, we get that the contribution for specific heat capacity from phonons is equal to this long expression here. So I had a feeling I made a mistake. That number there I put as S. It's actually a 5. I just have not the best handwriting on my notes. So this value here is approximately equal to some beta term t cubed. Now, what I would say for a test or exam, it's okay if you don't remember this. This is a super long expression. We will probably be given this beta term. And so all you really need to know is that the contribution to specific heat capacity due to phonons is equal to beta t cubed. I think that's fair enough to say. And this t cubed conforms with our red line very well. Now, it's seen, actually, that as we approach lower temperatures, our contribution from phonons begins to stop. But we still have a little bit of heat capacity. This heat capacity is given to us due to electrons. So we can say the total heat capacity is equal to the phonon contribution plus the electron contribution. Now, when we're talking about our reasoning for our electron contribution, we can use the same theory as before. The density of states along with our energy. Meaning that only the electrons close to the Fermi level can contribute when we're talking about specific heat capacity. Only these electrons can contribute. Now, this gives a little bit of a lengthy derivation, which I'll kind of go over, but it might not be as important as our final answer is going to be. So we know that our kinetic energy is equal to 3/2 Boltzmann constant times temperature. We remember that from the classical theory. Multiplied now by our number of electrons, right? That Dn. This is the number of electrons that we have at the Fermi level. Now this Dn, if you remember from earlier, is equal to the density of states at the Fermi level, right? Times that dE term. Now, if we were to take the derivative of this with respect to t, we would get Cv is equal to 3 Boltzmann constant. Sorry, this is my mistake. Going back to the kinetic energy question, or kinetic energy, we get kV squared T squared. This is because going back to this Dn, we're turning this dE term into our thermal energy term. And we're multiplying that thermal energy by our density of states. So Dn is equal to our density of states, which I'm using N and E are N and Z are interchangeable. Density of states at the Fermi level times the thermal energy at the Fermi level, which is going to give us the number of electrons that we want. Now, if we take our derivative with respect to T from here, we're going to get 3 kV squared T times the density states at the Fermi level. Now, this can be also approximated to some gamma term multiplied by T, a linear term. Now, if we don't know what the density of states is, we're going to use this term. We're going to say that the density of states is equal to 3/2 times the number of electrons with our energy less than or equal to the Fermi level times the energy at the Fermi level. If we then plug this into our density of states equation and use our Pauli exclusion principle, we get this is also equal to pi squared over 2 times Avogadro's number times Boltzmann constant T over the Fermi temperature. Now, this isn't as important as the first equation. So this is more so because it was derived in the notes, so it might be important to us. I think this is the most important equation here. Now, the thing that is super cool about this now is we can get an expression for our total specific heat capacity being equal to, if we for our electrons sub in gamma T, and for our phonons beta T cubed, we can then rearrange and say our specific heat capacity over temperature is equal to gamma plus beta T squared. Now we're going to plot this as a linear term. So we're going to plot our specific heat capacity over temperature with respect to T squared. If we do this, we get a y-intercept of gamma and then a linear function with the slope beta. And what's really interesting about this now is it gives us a way to find our density of states without calculation, right? Or sorry, find our density of states through direct experiment. So if we can find what our gamma is, we know this is equal to 3 Boltzmann constant squared times our temperature, not times our temperature, times the density of states at the Fermi level. So we can find the density of states at the Fermi level by taking our gamma term, whatever it is, and dividing it by 3 kb squared. If I were to guess, this would definitely be a question on an exam. All right. Now going on to our last topic, we're going to talk about thermal conductivity. We're going to begin this topic by talking about this thing that we call heat flux. It describes how well heat moves through a material. This heat flux is equal to a K term times the gradient of our temperature with respect to X. This is the rate of how temperature moves through our material. And our K term is equal to our thermal conductivity. And this thermal conductivity, just like our specific heat capacity, has a term from phonons, and it has a term from electrons. So let's take a look at what it looks like. Our term with the contribution from electrons includes the number of electrons times our velocity times our constant there, our K constant, that being Boltzmann, times the mean free path of electrons divided by 2. This is also equal to 1/3, this is the more common term, 1/3 of our specific heat capacity from electrons times our mean free path of electrons times our velocity of electrons. This is because if you take a look at our term for electrons here, it is 3 kb squared T times N. If we plug in our specific heat capacity for electrons, it's the same thing. It's very similar. The term that we use for the most part is this one here. The same for phonons. Now, we're going to use the same quantum mechanical correction as before. Only the phonons close, or sorry, only the electrons close to the Fermi level can be used in thermal conduction. When we do this, we use our Pauli exclusion principle along with the quantum mechanical term for our specific heat capacity. And we get this. Contribution of electrons is equal to pi squared, the number of electrons at a Fermi level, Boltzmann constant squared times our temperature, multiplied by tau, our relaxation time, divided by 3 times the mass. When we compare this to our normal conductivity, it's equal to the number of Fermi electrons, E squared, over mass times tau. Sorry, number of Fermi electrons. This means we can take our K over our conductivity there, and that's going to give us some constant term. Multiply our temperature. This is the Wiedemann-Frenz law, and it states that given thermal conductivity, temperature, and this constant term, we can find our normal conductivity. Or given a temperature and our normal conductivity, along with obviously the L constant, we can find our thermal conductivity. The final thing we're going to talk about is the contribution due to phonons. And we know that's equal to 1/3 specific heat capacity of phonons, velocity of phonons times mean free path of phonons. Now that we know our specific heat of phonons is proportional to T cubed. So I would say that means our K, our thermal conductivity should also be proportional. But this is wrong. So what do we know about phonons? Well, we know when we have an increased temperature, we have more phonons. Meaning we have more energy. And with a lower temperature, we have less phonons, so less energy. Now, what do we know about our energy? Well, we're going to talk about the kinetic energy because that's the energy of our moving phonons. And we know that's equal to 3/2 times our thermal energy. And we know that that thermal energy is equal to h dash squared times the wave vector of our phonons squared divided by 2m. Now, if we have a high temperature, we have a high energy, meaning we have a high K value. If we have a high wave vector, that means we have a low wavelength. If we have a low wavelength, this is going to mean if we were to be given a wave, it would scatter more on a vacancy or a defect. Now let's use that same argument. If we were to have now a lower temperature, we would have a lower wave vector and a higher wavelength. Meaning if I were to now use this same argument, this wavelength would miss most of the defects. So at a higher temperature, we have a lower wavelength, meaning we have a lower mean free path. And at a higher temperature, we have a higher at a lower temperature, we have a higher wavelength, meaning we have a higher mean free path. So our phonons are going to be deflected less. This gives us this kind of relationship. Thermal conductivity due to phonons with respect to temperature increases and comes to a maximum at around 20 Kelvin and then drops as temperature moves on. All right. Now that is our complete overview of this course, 2Q03. If you have any questions, comment them down below. And I hope everyone enjoyed. Thank you. Like, subscribe, I guess. I'll probably be doing more of these review sessions for materials, science, and engineering-based courses. So if you like that, you like science, stick around. Thanks.